Okay, so now that we've seen how to determine the pH of volatile and strong base solutions, let's take a look at the vast majority of cases that we're actually going to encounter, which are the weaker acids and the weaker bases, and how we can apply some of the equilibrium concepts we learned back in the lab to study in a little bit more detail what's happening with these with the weak acids and the weak bases. So most, that's the first thing you need to realize is that most acids are weak. Okay, which means that they do not ionize uh, a complete extent. They only ionize to a limited extent in aqueous solution. And then when we look at the reactions, we're assuming that all of these reactions are happening in solution, and specifically in aqueous solution, where H2O water is the solvent. But that's the assumption that we're making unless specifically stated otherwise. The degree to which a weak acid ionizes depends on two things. It depends on the concentration of the acid, and it also depends on the equilibrium constant for the ionization. So we can represent what's happening in a weak acid because it is only ionizing for a limited extent in aqueous solution. You can think of it as an equilibrium type process. So here's our weak acid, HA. Again, A here is just the anion, whatever that happens to be. It's just a generic form in H2O. And then you know that we can represent that equilibrium using the reversible arrows. This is an acid, donates to H plus. H plus goes to the base, which is the H2O. H2O becomes H3O plus. Then it can be the base of the HA and A minus. So everything is aqueous except the water that we have. So when we write our equilibrium expression for this K equal to H3O plus and A minus divided by A times H2O. Now we know that the H2O, the liquid, its concentration is not going to change. We can move it to the other side and we have our constant originally. We have a K times H2O, a constant K times another constant H2O. The concentration of H2O is going to give us our brand new constant now that we're going to designate as K with the subscript A. And the subscript A here represents it's a specific type of equilibrium constant. Here it's referred to the acid ionization constant. We saw Kw, for example, the ion product constant for water in the previous sections. Now we have Ka, and that is equal to H3O plus times A minus divided by the concentration of our weak acid HA. Now, when we look at this equation, right, this is something that we know how to write. We practice it an infinite number of times in the last section. We can look up, and these values are actually tabulated, values for Ka, right? And we know how to interpret these values now, so we know how equilibrium works. The larger that Ka value is, that means that the larger the value is in the numerator. So larger Ka means that we have a larger value. Well, what's in the numerator? The numerator is in the product side. Right, so if we have a huge amount of products, that means that this reaction here lies to the right. So we have a product and reactants. And as a result, if we have a lot of product, that means we have a higher concentration of H3O plus. And as a result, that is going to be a stronger acid. So a larger Ka means we have a stronger acid. And then conversely, a smaller Ka is a weaker acid. So we can compare strengths of acid just by looking up their Ka values. So the strength of the degree to which that acid ionizes depends on the equilibrium constant, ionization constant, it also depends the uh, on the concentration of the acid itself. All right. So for example, we have here two different weak acids. We have HF hydrofluoric acid and acetic acid CH3COOH. We have the equal concentrations of both of these. As you can see, the Ka values are different. So 7.1 times 10 to minus 4, it's a larger value than 1.8 times 10 to the negative 5. This is smaller, but the larger the Ka value, it's going to be stronger acid, which corresponds to a lower pH. Similarly, the smaller Ka value corresponds to a weaker acid. The pH is higher. And as a comparison, if we compare that to a 0.1 molar solution of a strong acid HCl, and this is strong now, we know that the pH, we can calculate the pH of that 10, or sorry, negative log of the concentration here, that ends up being 1.0. So you get a much stronger acid compared to the weaker ones, HF and CH3, COOH. So these are just two. There's, like I mentioned, the majority of the acids tend to be weak ones, and here we have a list of a few of them in order of stronger to weaker. Right. So these are weak acids to begin with, and within this collection, we have stronger weak acid versus weaker weak acids, and we can simply look at the Ka values to compare them. So 10 to the negative 2 is a relatively larger value compared to, for instance, phenol down here with a 10 to the negative 10, right? That's a 10 to the 8 magnitude difference between them. So as a result, we would predict them that the full acetic acid up here is going to be a much stronger acid. Even though it's weak, it's going to be a much stronger acid than the phenol. And that's a super weak acid in comparison. Okay, so the ionization constant, the acid ionization constant Ka, is a quick way to compare strengths of acids.